We will continue with the construction of the soft collinear effective theory Lagrangian. Let me just remind you that by the end of yesterday's lecture, we had discussed the collinear quark field. Where we basically took the QCD field restricted to collinear momenta and split it up into two spinors, xi and eta, for the collinear quark, where these spinors were chosen such that n slash on xi yields 0 and n bar slash on eta also yields 0. And n slash on the spinor equals 0 is the form of the equation of motion in the infinite energy limit. So this xi field is the field that we will be using later to describe collinear quarks. And we had derived also the power counting already, that Cn is of order lambda and eta n is of order lambda squared, both of which were different from the canonical scaling, which would suggest lambda to the 3/2. So this was an example of a power counting in an effective theory that's not the one from naive dimensional analysis. We'll discuss the collinear gluon field next. So the logic is we'll first discuss the scaling of the fields and their power counting, and then basically we'll start from the standard model Lagrange and apply this power counting and see what we get as interactions at leading order in lambda. For the gluon field, looking at the 2-point function in the way we have always been doing it, so time-ordered product of two gluon fields, polarization mu, color A, collinear gluon field, so fields restricted to collinear momenta, nu B for the second one. This is just the momentum space propagator, D for P over 2 pi to the 4th. Sometimes I'm using P, sometimes K. It has absolutely no meaning. It's just a random. What's the gluon propagator? Well, it's diagonal in color, 1 over P squared plus I epsilon. And I'm not using Feynman rule. I'm writing it in the most general form in arc-C gauge, where the propagator has a minus G mu nu plus 1 minus xi P mu P nu over P squared. And I guess if I have the indices up here, I should also have them up here. Now, for a collinear momentum, remember P mu has scaling lambda square 1 lambda in terms of Q, the hard scale. So D for P is again going to be lambda to the 4. 1 over P square is 1 over lambda square. And now you could say, well, and in fact, there was a paper where this was done, but it was incorrect. You could say, let's work in Feynman gauge. C is 1. G mu nu has no scaling. So the collinear gluon field just scales like order lambda, and we are done. But you see, this doesn't work anymore if we use a general gauge where the second term is also there. And the second term, of course, has various scalings, right? Depending on which components of the momentum we look at here, because this is the scaling of the different momentum components. So we need to look in detail at the various options here. And the first one, well, of course, what we can do is for the gluon field, like for any other vector, we can decompose this as n dot A times n bar mu over 2 plus n bar dot A times n mu over 2 plus A perp, like we did for any other 4 vector. And really what we'll find is that these different components also will have different scaling with lambda. So let's look at the various options. We can look at the 2-point function of two n dot a components. And I guess I should add color indices here. We get d4p, 2 pi to the 4th, e to the minus ipx. And now, well, we just need to take this expression and multiply with n mu, n nu. And then here, the first term gives minus n squared, which is 0. And the second term has n dot p squared. So we'll get here simply 1 minus c n dot p squared over p squared. This is lambda to the 4. Sorry, I forgot this propagator here. So delta AB p squared plus I epsilon. So here we have a 1 over lambda squared. And here now n dot p is the small component. N dot p counts like lambda square. So this is lambda square squared over p square, which is lambda square. So this whole expression counts like lambda to the 4. And we can do the same thing with n bar dot a. And let me just be brief here, d4p, 2 pi, the exponential. Same thing here, n bar squared is 0. So the only difference really is that here now we get n bar dot p squared over p squared and then delta AB over p squared. And n bar dot p is the big component. That's the order 1 component. So you see, instead of being lambda square in this case, this is now 1 over lambda square. And then we have 1 over lambda square from here, lambda to the 4 from here. So we find that this is actually unsuppressed, 0th order in lambda. Okay, and then finally we can look at the perp correlator, a perp mu, a perp nu is again d4p, 1 over 2 pi to the 4, e to the minus I px. And now here we get 1 over p squared plus I epsilon. And here now we have the perp components of the matrix, so minus g mu nu perp plus 1 minus xi p mu perp p nu perp divided by p squared. And now the counting is such that the measure is again lambda to the 4. This is again 1 over lambda squared. This has no power counting, and here we get lambda lambda over lambda squared. So this is also order 1, and you see that we get in total lambda squared as a counting. So based on this, we find that n dot a collinear counts like order lambda squared. That's the first relation. 2 of them give lambda to the 4. N bar dot a collinear counts like 1, and a collinear perp counts like lambda. It's not gauge dependent, no. This is the scaling relations that you derive for general xi. What I was saying is you could make the mistake that you say, let's pick xi equal 1, and then you only get the first expression, and then you could conclude that the gluon field scales like lambda, but it would be a wrong conclusion, because as you can see here, this first term for xi equals 1, it doesn't contribute here and it doesn't contribute here. So all you can really conclude is that the perp components scale like lambda. In order to see how the longitudinal components scale, you have to look at the general gauge. No, xi equal 1, the first two equations don't exist. It simply tells you this is 0, this is 0, so it doesn't tell you how these things scale. Yes. So if you want to have this in the back of your mind, let me write it generically. If I have a collinear field, think of the mode expansion, right? So this is d3p over 2 pi cubed, 2ep, and now e to the minus I px, and then you have, you have a term with annihilation operator. Sorry. And then you have a term with the creation operator. And just, if it helps you, what is a collinear field? It's a collinear field where somehow we put a theta function here, which is 1 only if P has a collinear scaling. So we can imagine in our heads to take the whole momentum space and split it up into a region where the momentum components have collinear scaling. In practice, we'll never do this because DimReg does the same for us after we expand in the method of regions, but conceptually, this is what we should have in mind. Now, what are these relations? They should look familiar. What are these? So these relations, first of all, tell us that not all components of the gluon field have the same scaling, which is, again, not what we naively expect. But what are these relations? What do we see? They are the same as the collinear momentum, okay? They are the same as the collinear momentum. So same as for the collinear momentum. By the way, if you looked at 2-point functions of mixed correlators, like one of these, or one of these, you would find that they all are compatible with these scalings. Now, why is this important? This is crucially important because the covariant derivative for a collinear field is, of course, so I d mu collinear, but this means really the covariant derivative acting on a collinear field. That's the ordinary derivative. And then it has the gauge connection, GS A collinear mu A times TA. It means that this term, which will produce from an incoming particle the collinear momentum, and the gauge term, they have the same scaling, okay? So this covariant derivative has, we say, homogeneous power counting. And this is crucial. What is the power counting? The power counting is usual, 1 lambda square, 1 lambda. And this is crucial because if this term had a different power counting from this term, it would mean whenever we have an expression with the covariant derivative, now we have to expand in lambda, and we would take these two terms apart, and that would break gauge invariance, okay? So it's very natural that it comes out like that. It has to come out like that, otherwise something would be inconsistent with our construction. Good, that looks completely beautiful. There is, however, a really worrisome feature at this point. namely the existence of an unsuppressed field this unsuppressed field is n bar dot a collinear, which counts like 1, is worrisome. Why is it worrisome? Normally, when you construct effective theories and you discuss the power counting, in almost all cases, you will find that each field, each derivative, each object in the theory has positive lambda counting. There are some exceptions when you look at 1 + 1 dimensional QFTs. But for instance, if you analyze scalar field theory in more than 1 + 1 dimensions, you will find that the fields always have positive power counting. And including the standard model, right? We know that scalars have dimension 1, fermions 3/2, gauge field dimension 1. And that's important for the SMEFT, for example. The SMEFT contains arbitrarily complicated operators built out of covariant derivatives and standard model fields. Standard model fields have positive power counting, derivatives have positive power counting, which means that if I add operators, if I add fields to an operator or derivatives to an operator, the operator will become higher and higher order in power counting. So it will have more and more suppressions with a new physics scale. And if we don't have that feature, you can ask what type of an effective theory is that? Here I have an unsuppressed field. So in other words, you give me an operator in SCET. I add 13 of these gluons to it, and that's an operator with the same power counting. So in other words, you immediately see I have infinitely many operators with the same power counting, and that's troublesome. No, you should say, well, wait a second, this cannot be correct. You did something wrong. We'll see what the way out of this is, but I just want to point out to you that this is a worrisome observation at this point. We will see that this is the reason why this becomes a non-local theory, basically. Yes, it has to be like that because otherwise the two terms in the covariant derivative would have a different power counting. And then once we expand in lambda, we would break gauge invariance. So it always has to be like that. Nevertheless, I mean, of course, we have to convince ourselves that it really is like that. Okay, so this is the collinear sector. What about the ultrasoft sector? In the ultrasoft sector, no surprises. First of all, the ultrasoft momentum has homogeneous power counting, all components scaling like lambda squared. So the Lagrangian in the ultrasoft sector is just the ordinary QCD Lagrangian. There's nothing to expand. And the power counting will just be the naive power counting that you would expect. So if we look at the power counting for ultrasoft quarks, P4P over 2 pi to the 4th, e to the minus IPX. And now here, I'm always setting the masses 0 for today. P squared plus I epsilon. Remember that now P ultrasoft, all components scale like lambda squared times Q. So here I have 4 components that makes lambda to the 8. And here I have essentially 1 component upstairs and 2 downstairs. So this is like 1 over lambda squared. So this scales like lambda to the 6, which means the ultrasoft quark field scales like lambda cubed. And remember that the ultrasoft scale is lambda squared. So this is really, if you wish, lambda squared q to the 3/2. Right, this is the ultrasoft, this is, if you wish, lambda ultrasoft. And you see it's just the ultrasoft scale to the 3/2, which is naive canonical power counting, okay? And the same for the gluon. again the gluon propagator in an arbitrary gauge. But there's nothing inhomogeneous now. All components have the same scaling. So the second term here counts like 1. This counts like lambda to the 8. This counts like 1 over lambda to the 4. This gives lambda to the 4, and it simply means A ultra soft mu scales like lambda square, which is really, if you wish, the ultra soft scale to the first power. So again, this is what you would expect from naive dimensional analysis. But okay, we have all these scaling relations for the gluon, for the collinear quark spinner, and for the ultra-soft gluon. And what we're going to do now, and this is a bit cumbersome, but it's not complicated. So it's important that you learn to distinguish difficult from cumbersome. Almost everything is cumbersome in theoretical physics, but it's not difficult what we're going to do. So basically, we start from the Dirac-Lagrangian. QCD is Dirac-Lagrangian plus Yang-Mills Lagrangian, of course. But we typically discuss the fermion sector because it's non-trivial, because in the fermion sector we are actually going to integrate out something, namely this eta field. In the gauge sector, you can write it down, but it's, there's nothing interesting, nothing very interesting happening. So I'm going to discuss the quark sector in detail. So we start from the Dirac-Lagrangian for a collinear fermion, and we now introduce. So we perform the decompositions that we write psi equals to xi plus eta with power counting lambda and lambda squared, and that we write the gluon field, which sits inside the covariant derivative as a collinear gluon field plus an ultrasoft gluon field. But the collinear gluon field has mixed power counting, lambda square 1 lambda, depending on which component you look at. And, oh, I'm sorry, I forgot the most important. So, and lambda squared here, and I forgot here, of course, sorry, I forgot here the ultrasoft quark field. This is also there, of course. So this is lambda squared, this is lambda cubed. And I mentioned last time there's also an anticollinear sector, but we had this symmetry that, only the collinear and the ultrasoft interact and the anticollinear and the ultrasoft interact, but the Lagrangians are copies of each other, just with n and n bar interchange. So I'll just focus on the collinear sector for now. And this was also nonsense. I should really start from the full Dirac-Lagrangian. And now I split up every field into a collinear and an ultrasoft piece. And that's it, okay? So it's not more than that. So we get psi bar ID slash psi. And by the way, you can ask, what about the mass term? Please write down the mass term. It's going to be exercise 2 on problem set 2, which comes tomorrow. And it's a very easy exercise. You can already do it today if you want, but it will be an exercise. So, we really just try it out. Let me write the derivative as collinear plus ultrasoft, and I think it's clear what it means. It means that the gauge field is given by the sum with ID slash collinear plus ultrasoft is equal to ID slash. No, I want to write it differently, sorry. I want to decompose it into light cone components. So first of all, we have the n dot d, and I'm writing d now as d collinear plus, and then the ultrasoft field I need to put separately. So d collinear means the covariant derivative just including the collinear gauge field, like here. This is d collinear, and now the ultrasoft piece, I need to add it separately. And this comes with n bar slash over 2, and then we have a similar term, which is n bar dot d collinear plus g sub s n bar dot a ultrasoft times n slash over 2 plus the perp components. Plus GSA ultrasoft perp slash. Okay. What's the power counting? This is lambda squared. It's the small component of the collinear field. This is also lambda squared. This is 1. This is still lambda squared because it's an ultrasoft gluon field. This is lambda, and this is lambda squared. So you see directly, not all components of this derivative have the same scaling because we're mixing together ultrasoft and collinear stuff. But also not all components of the spinors have the same scaling. So we really need to collect terms now. Okay? Now, you find that the leading terms are order lambda to the 4. And these order lambda to the 4 terms are the following. If you start with the biggest, so here we have lambda, lambda squared, lambda cubed. If we start with the biggest spinor components, xi bar and xi, then we have lambda and lambda. And now, however, remember that xi is annihilated by n slash. So this n slash term between two x's, it will project to 0. This term exists. So we'll get an n bar slash over 2. And now this expression, I n dot d collinear plus g n dot a ultrasoft times xi n. This is a term of order lambda to the 4. Capital D is a covariant derivative, is this object. Too many people now. What exactly is the question? Exactly. So the collinear part I collect in this capital D symbol. So because it's reasonable because this thing has homogeneous power counting, but this has different power counting sometimes, like here and here. So I split these up because they have different power counting. Okay, so this is the first term, the xi and the xi, and also this term vanishes. Also this term vanishes because if we have xi eta and some transverse gamma matrix, Cn, this is 0. And the reason is that, remember, these Cn's, they contain projection operators. So the projection operators are n bar slash n slash over 4, gamma mu perp, n slash n bar slash over 4. And in this case, since this is a perp object, you can move this n slash through here, and then you get n slash, which is n squared, which is 0. So this term vanishes between two x's. This term vanishes between two x's. This is the only term that survives. The next term is the one if we take two etas. So eta n. Now the eta is annihilated by n bar slash. Okay, so this term doesn't contribute between two etas. This term does. but in eta it's already lambda square. So if I have two etas, I already have lambda to the 4. So I'm only allowed to keep the order 1 term here. So here I get n slash over 2 I n bar dot dc eta. Let's do the mixed terms. 1 xi, 1 eta. So if I have 1 xi, 1 eta, the xi is destroyed by n slash, the eta is destroyed by n bar slash. So the only thing that survives is the perp terms. However, the xi has order lambda, the eta is order lambda square counting, so I already have lambda cubed. So I'm only allowed to keep the first term here to get lambda to the 4. Okay? So I get here d slash collinear perp eta plus Hermitian conjugate eta d slash collinear perp c, and that's it. If you try to involve an ultra-soft quark, you will immediately see that you get lambda to the 5th. So this is the leading order contribution, and you see the leading order contribution has only collinear fields in it, no soft fields.
When you wrote the cyber ID slash at the reactor end, right?
Yes.
So this D slash involves all momentum configurations.
Yes, collinear and ultrasoft.
And then, but when you were writing the DC is scaling as lambda square 1 lambda, right?
Lambda square 1 lambda, yes.
But there is a, what about all those momentum scales as 1 lambda square?
Now that's the anticollinear.
Yeah, anticollinear.
I said that we're discussing the collinear sector because last time we had this picture that the Lagrangian will have this structure, collinear, anticollinear, ultrasoft, and there are interactions here and interactions there. So I'm only discussing this part of the story. And this part of the story, you just exchange collinear with anticollinear, just the labels. Good question. Thank you. Good question. So order lambda to the 5th, let me just give you the answer. You can easily figure it out for yourself. Order lambda to the 5th, you get the following terms, Cn, Gs, A ultrasoft perp slash eta n plus Q ultrasoft Gs A perp collinear Cn plus Q ultrasoft n slash over 2 n bar A collinear eta n plus everything Hermitian conjugate. And let's just check that the scalings are correct. This is lambda squared, this is lambda squared, makes lambda to the 5th. This is lambda cubed, lambda makes lambda to the 5th. This is lambda cubed. 1 lambda squared also makes lambda to the 5th. And if you look at it, you'll find there are no more terms. Then there are terms of order lambda to the 6 and higher. In fact, the highest you get is lambda cubed from here, and lambda cubed from here, and lambda squared from here, which is lambda to the 8. Okay, so this goes on until lambda to the 8. Now, notice that as soon as we go beyond the leading order, we have at least one ultrasoft field. So the statement is that if I only look at the collinear Lagrangian, no interactions with the ultrasoft sector, if I only look at the collinear Lagrangian, the order lambda to the 4 term is exact. And that's very reasonable that it should be like this, because I have not integrated out anything yet. I have just rewritten QCD in terms of new definitions, xi eta. Okay, so I've not done anything to the theory. This is still completely full QCD, nothing integrated out. I'm saying if I just look at the collinear fields, not ultrasoft ones, if I just look at the collinear fields, this is exact. You will not find at higher orders any term that has only collinear fields. You will find terms that have collinear fields and at least one ultrasoft field. That was all I was saying. So, in other words, we can now write the Lagrangian in the form corresponding to this picture there. I can write L-SCET as L collinear, which means only collinear fields, L ultrasoft, which means only ultrasoft fields, and then interactions terms, collinear and ultrasoft. And I could add the anticollinear and the anticollinear plus ultrasoft if you wish also here. But we are not going to discuss those because they look identical as these ones. Now, the action is, of course, the space integral over this Lagrangian. So let me write it in this form for reasons that will be clear in a moment. Now, we have to assign, when we want to know how the action scales, we have to assign scaling to x. And the right way to assign scaling to x is to think about the phase factors that we have when we write down the fields or the Feynman rules, right? Everything we do, the propagator, etc., they all come with these plane wave factors. And for instance, if we have an ultrasoft momentum here, then p square counts like, for the ultrasoft, counts like lambda square. And then you would always require that the phase factor should be order 1. If the phase factor is not order 1, if it's much bigger than order 1, then the phases oscillate like crazy and the contributions will average out to 0. So P ultrasoft of order lambda means X ultrasoft of order 1 over lambda squared. And P collinear of order lambda square 1 lambda means X collinear of order 1 over lambda square 1 over lambda. When I take a scalar product, this goes together with this goes together with this, and this goes together with this. Now, whenever I have collinear fields in a Lagrangian, the scaling of the Lagrangian is set by the collinear dynamics, so I need to apply this scaling. So the D for X collinear, which sits here, scales like 1 over lambda to the 4. Whereas if I have the ultrasoft Lagrangian with no collinear fields present, then this is 1 over lambda to the 8, because it's 4 powers of 1 over lambda squared. Yeah. And you will see why that is reasonable in 1 second, if you allow. So just wait a second, please, because just want to finish this argument. So the purely collinear Lagrangian we thought was lambda to the 4. The interactions with the ultrasoft, actually the first such interaction is here. So it also starts at order lambda to the 4, but actually it can be lambda to the bigger than or equal 4. Okay? And the ultra-soft Lagrangian itself, you can easily convince yourself, is purely lambda to the 8. Just write down the Q bar ultra-soft, D slash ultra-soft, Q bar ultra-soft is lambda to the 8. So you see that this term of the action is order 1. This term of the action is also order 1. And this term of the action is order 1, lambda, lambda square, and so on. So basically, the leading terms are order 1, and then there's higher order corrections. And this is reasonable, right? This says the leading order in the effective theory gives the order 1 contributions to the action, always in units where h bar is set to 1. But then if you have an EFT expansion, there will be power corrections of order lambda, lambda squared, but they only come in the interaction of collinear plus ultrasound. So now the questions. Yeah. This is not just an EFT. This is also what you do in QFT. Because we have the action functional, and basically large contributions to the action are order 1 in units of h bar, right, in the quantum world. So this is just, you assign this scaling because it's very reasonable in terms of these phase factors, but it's also defined, you get the same scaling by requiring that the leading terms in your expansion give order 1 contributions to the action and everything else is power suppressed. Good. So now we have just done power counting. Not constructed anything yet. We've just introduced power counting for the gluon fields, for the quark fields, and decomposed the Lagrangian in terms of leading terms and subleading terms. Okay. Now we are going to we will use C as an interpolating field. For a collinear quark. Really, the quark spinner is Xi plus eta, but we have already seen that eta is power suppressed. Eta is of order lambda square, Xi is of order lambda. So it's very natural to eliminate eta from the theory. Again, you should not think of this as integrating out some physics, because we'll really just eliminate it. We'll eliminate it exactly to all orders. In the case of HQET, when we eliminated capital H, it gave rise to an infinite series of terms. And then when you truncate, it's really like removing something from the theory. Here, as you'll see, we'll not get an infinite series, we'll just get a solution. And we'll just plug in that solution. So the Lagrangian we will obtain is 100% equivalent to this Lagrangian. Nothing has been integrated out. It's just a rewriting in terms of new field variables. So think of it as a change of variables more than integrating out some heavy physics. In that point of view, it's different from HQET. So where does eta enter? Well, you see eta enters here and eta enters here. If you look at this expression and you forget about the ultrasoft field for the time being, it looks kind of similar to HQET. You remember we had little h, capital H, and then the mixed terms. The mixed terms look exactly like in HQET, only that the meaning of perp is different in the two theories, but never mind. Here in the case of HQET, we had v dot d, and here we had the mass term. We had 2mq plus v dot d. That is different. We don't have a mass term here. But the structure of this Lagrangian, in particular, the fact that it's quadratic and you can do the functional integration over the field eta, is completely equivalent. I'll do it here. Let me not use functional integrals. I'll use the pedestrian way. I'll solve the equation of motion. So I take just the collinear Lagrangian now, take the variation with respect to eta bar. And since no derivative of eta bar enters, I can set this to 0. This is n//2 I n bar dot d collinear times eta plus I d slash collinear perp times xi is equal to 0. We had a very similar equation for HQET, except that the first term had the 2mq there. And then I said, let's just invert the equation. We will also invert this equation. But in order to invert this equation and solve it for eta, we need to divide by this differential operator. And differential operators can have 0 eigenvalues. So therefore, I'm going to add a regulator here. So let me write this as n//2 I n bar dot dc plus I delta. Going to add a small regulator here. Times eta c is equal to minus n bar //2 I d perp collinear times c. Now I'm going to multiply this equation with n bar //2. Oh no, sorry. This is not here. Now I'm going to multiply, so the equation is like this, as you can obviously see, sorry. Now I multiply with n bar //2 on both sides. And now here you can see this is what I called the projector Pn bar last time. There's no Dirac structure here, so this is Pn bar acting on eta, but eta is defined as Pn bar acting on psi. And since Pn bar is a projector, I can apply it as many times as I want. It just projects always back on eta. So basically you can put this to 1 and you get the equation that this is equal to this. And now with the delta in place as a regulator, I will just solve for it. And the solution will be eta n is equal to minus n//2, the inverse of n bar dot d collinear plus I delta I d slash collinear perp acting on xi. And if you go back and look at HQET, in the case of HQET, we had a similar result, but not quite the same. Capital H was given by 1/2 mq plus I v dot d soft I d perp s dagger times little h. Okay, and many similarities. You see the perp derivative here, it's also there. But the key thing was here we had a large mass in the denominator. This is a small soft momentum, so we could immediately power expand here, and that is what generated the series of terms of order lambda QCD over MQ to ever higher powers. That is the heavy quark expansion. Here we don't have that. We still, if you look at the power counting, C is order lambda, perp derivative is order lambda, n bar dot d is order 1, that's the big component of a collinear object. So you see that eta is order lambda square, it's power suppressed, because this is order lambda, this is order 1. similar to here. This is order lambda, this is order 1. But the order 1 here is a momentum. It's not a mass. Plus, there is no small correction here. The small correction, if you like, is the ultrasoft field. If I would keep it, I would get the ultrasoft field there, which would be power suppressed compared to that. And that's the reason why I have expanded it out. Okay. So, for the moment, let's close our eyes and not, of course, you should ask me, what exactly do you mean by this inverse derivative? And I'll tell you in a little while, in a little moment, actually, in a couple of, before the break, I'm going to tell you. At the moment, it's a formal, sorry, I don't see you. Where? Oh, yes, please. Yeah, so I think of it as a variable, a change of variables, because when we say in the EFT language, when we say we integrate out something, it means we really remove some short distance physics from the theory. But here it's not what we do. Here we introduce a new variable instead of psi. I use xi, but I'm doing that transformation exactly. So the thing, I write psi as xi plus eta, and then I solve for eta by solving the equations of motion, and I plug the solution again in. And if that would now generate an infinite series, and I would stop at the second term, then I had really neglected something, okay? But it's not what happens here. This Lagrangian, well, I haven't written the Lagrangian. Let me plug this solution in, and then we get the SCET Lagrangian. This SCET Lagrangian is exact. And there's no, there's no ratio of large scale over small scale. The collinear SCET Lagrangian has no large and small scales. And therefore, it's really just a rewriting. However, later, when we study applications of SCET, if I now have, let's say, you give me a weak interaction operator for some transition, B to pi or whatever, and now I have a collinear quark there, and now I write for the collinear quark C plus eta, at that point, the eta is a power correction. And there I will really neglect it, or if I work to subleading power, I will include it as a power correction. But at the level of the collinear Lagrangian, there's no power expansion. We're doing exactly, we're just reformulating the Lagrangian. So if I insert eta into LC, I get the following expression for the purely collinear Lagrangian. Now at leading, well, for the purely collinear Lagrangian, it's exact at order lambda to the 4. And I get xi bar n slash over 2 I and d sub c c. And the next term I get is minus xi bar I d slash collinear perp n slash over 2 1 over I n bar dot dc plus I delta. Delta was my regulator, which I need to invert this differential operator. This. I get two terms, like in HQET, before we do the expansion, but here there's nothing to expand. This is the second term. You can easily see, looking at this expression, you see that for each term, if you insert this solution, you see that these three terms will simply combine to give this one term over there. And then, of course, what I should add to this is the pure glue terms in the Lagrangian. But again, they're not so interesting because the interesting stuff here is happening with the eta, which we eliminate. Now, what's the inverse of a derivative? You're almost always right, so shout it out. In mathematics, what is the inverse of a derivative? An integral, right? What's the inverse of a covariant derivative? No idea. Because it has a gauge field in it, so it's not just an integral, okay? Wouldn't it be great if we could turn a covariant derivative into an ordinary derivative? We have already done that once in these lectures, in lecture 2. The Wilson line did that trick, okay? So we're going to use the same trick again. So to define the inverse covariant derivative, we use the Wilson line. We use the trick of the Wilson line. It's really a trick at this point. In this case, it's a collinear Wilson line. It's not a soft Wilson line. The soft Wilson line we called S, the collinear Wilson line we could have called C, but the inventors of SCET called it W, like Wilson. So WC is a collinear Wilson line. And the collinear Wilson line is also a path-ordered exponential. It will look very much like what we wrote for the soft Wilson line. But now, here, you see the object we want to simplify is n bar dot the collinear gauge field. So we need n bar now, not n, times a collinear evaluated at x plus t n bar. This is the definition of the collinear Wilson line. And notice that what sits here in the exponent is the order 1 component of the gauge field. Okay, this component which is unsuppressed. That sits here in the exponent. So it's analogous to the definition of the Wilson line in HQET, except that it's now in the collinear sector, but it obeys the same set of mathematical rules. So we have the following rules, namely that the covariant derivative acting on that Wilson line and only on that Wilson line, so I put a bracket around it, is 0. And it's straightforward to show that in the same way that I ask you to show it for the soft Wilson line. Identical steps of calculation. When I write this, I really mean that in the sense of a differential operator, if I have n bar dot d collinear acting on the Wilson line times some other field, let's say phi of x, okay, and now you have the covariant derivative acting on w, that is 0, but what remains is the ordinary derivative part acting on the field phi, okay? So in other words, as a differential operator, I can write this as I n bar dot dc acting on the Wilson line, and whatever comes after it is the Wilson line times an ordinary differential operator. So this is another way of writing the same relation up there. And I claim that this implies that 1 over n bar dot dc plus I delta is equal to WC 1 over n bar ordinary derivative plus I delta times WC dagger. Let us prove this relation, and then sooner or later we have to break for t. So how do we prove this relation? I will work backwards from here to there. So let's assume this relation is true, and let's take this relation and multiply from the left with W dagger C I n bar dot dc, and then with the W dagger from the right. So we just apply this to this relation. And then you see on the left-hand side, this cancels this inverse propagator. So we get WC dagger, WC, which of course is 1. This is a unitary operator. On the right-hand side, we get WC dagger, I n bar dot dc, then WC 1 over I ordinary derivative plus I delta WC dagger. Now we use this relation that I n bar dot dw is W times ordinary derivative. So this is W times ordinary derivative. And now the W cancels the W dagger, the ordinary derivative cancels the ordinary derivative. Something doesn't square. Wait. Okay, I forgot this WC. Add this here. So you see, this is 1. This cancels this, and this cancels this. This is also 1. So these two things are really equivalent. Okay, so this is the equation we need, because if we use this equation here, it lets us turn an inverse covariant derivative into an inverse ordinary derivative. Okay, so let me just write this equation and then we come to an end. So LC now we have in the following form: C bar n slash bar over 2 I n dot d collinear Cn. And now the second term is minus Cn bar I d slash perp collinear n bar slash over 2. And now so now I use this relation, so I get a W, a Wilson line. Now an ordinary inverse derivative. Another Wilson line. And then my transverse derivative perp and Cn. Okay, so let me put parentheses around here. So now it looks more complicated because now all of a sudden these Wilson lines entered, but The main difference is that this inverse covariant derivative is now turned into an ordinary inverse derivative, and now you told me before that an inverse derivative is an integral, and that's exactly what it is. Now it is an integral. It is a line integral along n bar, and that's the last step now. Then we break because this is now the SCT Lagrangian for a collinear quark, n dot d collinear Cn, and now here I claim that this is equal to minus C bar I d slash collinear perp W of x. So I'm writing the Lagrangian at x, at point x, but here I put the x explicitly because you will see now that here this inverse derivative turns into an integral from minus infinity to 0 dt. And now this expression WC dagger I d collinear perp slash Cn at position x plus t n bar. Okay, so I don't know. It wouldn't be so hard to clean. I would use color. This is a very nice equation. This is the collinear Lagrangian for a quark in SCET. Everything is defined now, no inverse weird derivatives anymore, but we needed, you know, the price we paid for this is hefty. We need to introduce Wilson lines, whether we like it or not. Wilson line was the trick to turn the inverse covariant derivative into an integral. And the integral means that this is a non-local theory, right? In the first term, every field is at the same point. In the second term, we have a bunch of fields, field and Wilson line and derivative at one point. And now again, same field and Wilson line and derivative, but now integrated from the point x out to infinity along the direction n bar. So this Lagrangian is non-local. It's not a little bit non-local. It's maximally non-local, because this quark field and this quark field, they can be light years apart, but they're light years apart on the light cone. They're light-like separated. They're not time-like separated. That would violate causality. They are light-like separated. Okay? So in a way, the price is high you pay for eliminating this eta field. On the other hand, the eta field is power suppressed. So if we ever want to use this SCT, you know, somebody gives you an external operator with a collinear quark field. There, it's important to write it as Xi plus eta, because the two pieces have different power counting. And there we want to really then perform an expansion. But at the level of the Lagrangian itself, the price one pays is rather high, because it introduces this non-locality. But you know, this is the no free lunch, the famous no free lunch theorem. If you have a complicated problem, there might be different ways of dealing with it, but they are all complicated. It's a good point to have the break, and you can try to swallow this. If you follow step by step, every step is not difficult per se, but of course to go from, where was it? To go from here, which looked still very simple, to here, the Wilson line and the integral is just a way of giving meaning to this inverse covariant derivative. That's what it means. We'll put it in later. For now, I wrote the Lagrangian in this form, right? So for now, I was working on this guy. Next step, we will look at this guy. You're right, we'll put it back. And it's easy to put it back. It will be just added here. Will be just added here, plus GS n dot A ultrasoft. Because that's the only place. Okay. Because what is this thing? This thing is del plus A collinear plus A ultrasoft. So it's not that there are two derivatives. There's a derivative acting on all these fields, right? And then I have a collinear gauge field and an ultrasoft gauge field. I kept these two things together and called it decollinear because they have the same power counting, so there is no need to take them apart. But the ultrasoft guy has different power counting, so I needed to separate it so that when we looked at powers of lambda, it's treated differently, right? You see that here, for example, the collinear field enters, here it doesn't. And then it comes here, for example, right? So this is the term that in a way goes together with this one. You see xi eta, they go together, but this has a different power counting from this. So this is why this is in the order lambda to the 5th term, and the other piece is in the order lambda to the 4th. Yes, and that's true. That's true in this Lagrangian. This Lagrangian you will find is just the ordinary QCD Lagrangian. It has everything that QCD has, so you will just. Yeah, I mean, there are terms where you are right. There is a term where the derivative here acts on the ultrasoft field, absolutely. Absolutely. And there's even a term when you keep only the derivative here and the ultrasoft field. They're all there, but they come at higher orders in lambda. No, well, yes and no. The fact that I'm using the equations of motion makes it sound like a 3-level statement, but really I'm doing a Gaussian integral in the functional integral. So there is a determinant. The determinant is again a log trace of an infinite constant, so it has no field dependence. So no, the way I'm presenting it here using the classical equations of motion, it might look like it is a 3-level statement, but it's not. Actually, Anish, if he would have more lectures on EFTs, he would have taught you the theorem that using equations of motion is valid also beyond 3-level in an effective Lagrangian. You can use the equations of motion to reduce the basis in an effective Lagrangian, and even though this is the on-shell equation of motion, it works also in loop calculations. And the reason is because you can, implementing the equation of motion, you can describe it really as a change of variables, basically, as a field redefinition. And field redefinitions are always allowed. And basically what you can show is that they leave physical quantities, Green's functions, not Green, I mean physical quantities, sort of the on-shell Green's functions are invariant under such transformation. So it's not something that is corrected. In fact, there is a non-renormalization theorem which tells you that this Lagrangian is exact, has no power correction, and no renormalization. There's no renormalization in this Lagrangian. And the reason is simply, it is still the full Dirac Lagrangian. I have not thrown away anything. I've not neglected anything. It's the full story. And this is not renormalized beyond the usual field and charge renormalization that you also have in QC. Okay, it's high time for the break. Or more urgent questions right away. We also have the discussion session later, of course, plus the second lecture with questions. No, because in the Young-Mills part, I'm not eliminating an eta or anything. I mean, remember that the gauge field has different power counting depending which component you look at. But that's okay. I mean, there's still nothing to expand out in the Young-Mills part. Always think of, you know, if I have only this, where's my, if I only look at this Lagrangian, not coupled to ultrasoft, only look at this Lagrangian, it describes a world where all particles are collinear. So it's a strange word. All particles decide to move to the left, like an army, okay? But what does it mean? I just do a Lorentz transformation. I go to the rest frame, and I will walk in all directions, okay? So this purely collinear Lagrangian is completely equivalent to the QCD Lagrangian. It's just QCD boosted to a frame where all move to the left. That's not changing the physics. That's the reason, really. So there is really nothing to expand here. There's no large or small ratio. In HQET, we had lambda QCD and MQ. In this collinear Lagrangian, per se, just one collinear Lagrangian, we have no large scale. You can say, well, but the energy is bigger than the momentum. Yes, but only because I boosted to a frame where this is so. This is not a Lorentz invariant statement, right? I can boost to a frame where all momentum components are of the same order, and it's just like QCD, all scales are equal. So there's nothing integrated out, there's nothing expanded away, which is why this is exact, not renormalized, and in the Young-Mills part, you don't do anything, you just write it down. That's it. You just write it down. When we study external operators, weak interaction operators or whatever, in the context of this theory, whenever we have a collinear quark, we have to expand it as Xi plus eta, and eta is given by this solution, okay? So then we use the fact that eta is a power correction. For those external operators, eta will be a power correction. And then at leading power, we just use Xi, and at next to leading power, eta would come in. And eta, you know, this is basically eta. Eta you can write in terms of, again, a Wilson line with an integral, a line integral over t, etc. All these are very good questions. And this is also not easy stuff. I mean, this looks very complicated. Actually, the fact that this Lagrangian, as it is written here, is equivalent to QCD, we use all the time, because when you work in SCET, you almost never work with this Lagrangian. It's only important that it exists in a way. So if you, at least if I need to do a calculation with collinear fields, I always go back to QCD. I always write Xi is just the ordinary QCD field with an n bar slash over 4 in front of it and a Wilson line, and that's it. You just need to add the Wilson lines. And the calculations can always be done in ordinary QCD. And you'll also see in a moment why this is very useful. But I think at this point we should probably really break. 3:15, okay.